So hello students, continuing ionic equilibrium. This is our third lecture. In second lecture we discussed a lot of problems based on weak acid and we understood how to solve the problem based on weak acid, when to consider alpha, when to ignore alpha. So we are going to solve a couple of more problems of different type on weak acid solution, and then we'll start the weak base solution. So few more problems on weak acid. So in the series of weak acid, now let us take a situation. We have been given Ka of acetic acid (2 into 10 raised to the power minus 5) at 25 degrees Celsius. Now the question is, to what volume a 300 ml 0.5 molar acetic acid solution must be diluted in order to double its pH. So the question is, we have been given 300 ml of an acetic acid solution whose molarity is 0.5. So we want to dilute it till its pH is doubled. So the question pertains to first determination of initial pH, then we will have a required pH which will be double of the initial pH, and then we'll have to think how to reach to that point. So the first thing is to determine the initial pH. So let us calculate pH of the given solution first. So we have been given 0.5 molar acetic acid solution. Acetic acid being a weak acid, it will ionize to give H plus and acetate ion. So if we apply the approximate formula to determine the initial alpha, the alpha will be root under Ka by C. K and C are given, so K is 2 into 10 raised to the power minus 5 upon C is 0.5. So by inspection we can say that the value of this alpha is very small, it is smaller than 0.1. So it is negligible. In case of negligible alpha, we know that the concentration of hydrogen ion in the solution, will be root under Ka into C we derived in the previous lecture. So it will be Ka 2 into 10 raised to the power minus 5 into C is 0.5 and whole is under root. So it is 2 into 0.5 1, so root under 10 raised to the power minus 5. That is concentration of hydrogen ion of the original solution. So if we convert it into pH, it will be negative log of concentration of hydrogen ion, that is negative log of 10 raised to the power minus 5 whole raised to the power 2 for root. So it is going to be 1 upon 2 into 5. So minus of 5 when comes out with minus it will become plus. So it is 2.5. So the original solution pH is 2.5. Next is then a required pH. The question is to double the pH. So the required pH is twice of the given pH. So required pH is 5. This pH is going to be attained by diluting the solution. Now after dilution we don't know what is going to be the concentration of acetic acid. So in that case we cannot ignore or we cannot assume about alpha that it is going to be negligible. We don't know about alpha, we don't know the final concentration, so we can't apply the Ostwald equation. So what can be done now? We will be writing again the ionization of weak acid after dilution. So after dilution, acetic acid ionization will be written in the same manner to give CH3COO minus H plus. Now after dilution let the concentration of acetic acid be C. The C is the initial concentration of acetic acid after dilution. That means after dilution if we consider no ionization of acetic acid, C would be the concentration of acetic acid. So C is the concentration of acetic acid without ionization after diluting the solution. Now if alpha is the degree of ionization, so it will be written as C into 1 minus alpha. On the other side it will be C alpha C alpha. The final pH is given. So final concentration of hydrogen ion in the solution is 10 raised to the power minus 5. So this C alpha, which is the concentration of hydrogen ion in the final solution, is given to us. It is 10 raised to the power minus 5. So now if we write the equation of Ka, it will be C alpha into C alpha divided by C into 1 minus alpha. If we cancel 1 C and substitute C alpha from here, we obtain Ka is 2 into 10 raised to the power minus 5, and that is equal to C alpha is 10 raised to the power minus 5 multiplied by alpha upon 1 minus alpha. So if we cancel this 10 raised to the power minus 5, it manipulate as 2 into 1 minus alpha. 2 into 1 minus alpha is equal to alpha. So 2 minus 2 alpha is equal to alpha. So 2 alpha, 2 is equal to minus 2 alpha will become plus 2 alpha on the other side. So total will be 3 alpha. So alpha is now 2 by 3, which is much greater than 0.1. So, this alpha is not negligible. So, after dilution, we cannot apply simply H plus is equal to root under K into C, because alpha was not negligible and was not known also. So, we first determine alpha using the final pH of the solution. Once alpha is known, now this problem is solved, there is nothing more left in this question. So, alpha is known, so C alpha, which is 10 raised to the power minus 5, and alpha is 2 by 3. So, C will be equal to 10 raised to the power minus 5 upon alpha. Substitute alpha is equal to 2 by 3. So, it will be 3 by 2 into 10 raised to the power minus 5 molar. So, concentration of acetic acid after dilution is this. Concentration of acetic acid before dilution was 0.5 given in the question. Initial volume was 300 ml, final volume is required. So, now we can apply the dilution formula on acetic acid. So, M1 V1 is equal to M2 V2. Here we are equating the moles of acetic acid in the original solution without considering ionization with moles of acetic acid in the final solution without considering ionization. So, M1 is 0.5, V1 is 0.3 liter is equal to M2 is now known, 3 by 2 into 10 raised to the power minus 5, and V2 is unknown. V2 is unknown. So, with this we can solve it. V2 will be equal to 2 into 0.5 1, 3.3 0.1. So, 0.1 divided by 10 raised to the power minus 5, it will be 10 raised to the power 4 liter. So, this is our final answer. If we dilute the given solution to 10 raised to the power 4 liter, pH of the solution will be doubled, which is 5. So, this is the final answer. Let us take one more example of solution of weak acid. It is given that the concentration of sulfur dioxide gas in air over a city on a day is 10 ppm by volume. Also given solubility of sulfur dioxide gas, solubility of SO2 gas in water is 1.6 mole per liter per atmosphere. Also, pKa of SO2 is 2. Determine pH of rainwater that occur on that day. So this question is partly related to solubility of a gas in a liquid, which is discussed in Henry's law. And according to Henry's law, concentration of a gas. So first we'll have to find out the concentration of SO2 in the rainwater, and for that we'll have to use the relationship of solubility of gas with the Henry's law constant. So concentration of any gas is equal to partial pressure of that gas multiplied by the constant Kh, which is Henry constant. Here this constant is given. Also, mole fraction of SO2 in air can be determined as 10 upon 10 raised to the power 6. It is volume fraction, which will also be equal to mole fraction, since at same temperature and pressure volume is proportional to mole. So it is 10 raised to the power minus 5. If this is the mole fraction, then partial pressure of SO2 in air will be equal to mole fraction multiplied by total pressure. So total pressure is 1 atmosphere, so it will be 10 raised to the power minus 5 atm. So now partial pressure of SO2 is known, this constant is given, so concentration of SO2 in water can be determined. So molarity of SO2 in rainwater will be equal to its partial pressure multiplied by Henry's constant. Partial pressure is 10 raised to the power minus 5, Henry's constant is 1.6, so it is 1.6 into 10 to the power minus 5 molar. So now this is the concentration of sulfur dioxide in rainwater. Sulfur dioxide dissolve in water to form sulfurous acid H2SO3, which behaves like a weak acid and ionizes like this, for which pK is given, that means K is 10 raised to the power minus 2. So K is given, concentration is now known, so alpha can be approximated. If we apply the approximate formula for alpha, it is root under Ka, which is 10 raised to the power minus 2 upon C 1.6 into 10 raised to the power minus 5, which is much greater than 1. This indicates that alpha is very, very large. So alpha is very, very large, and acid can be assumed to be completely ionized. So if acid is completely ionized, if H2SO3 is completely ionized by this expression, initial concentration of H2SO3 was 1.6 into 10 raised to the power minus 5, and in case of complete ionization, hydrogen ion concentration will also be 1.6 into 10 raised to the power minus 5 molar. So pH can be determined by taking negative log of this. So pH will be minus log of 1.6 minus log of 1.6 into 10 raised to the power minus 5. So if we take negative log of this quantity, it will be 5 minus log of 1.6 can be written as 16 by 10. So it will be 5 minus log 16 is 4 log 2 minus log 10. Log 10 is 1, log 2 is 0.3, so 0.3 into 4 it is 0.1.2, it is 1. So 1.2 minus 1 is 0.2, so it is 5 minus 0.2, so 4.8. So this is the pH of rainwater. This was the question in IIT JEE 2000. At that time log table was allowed, so data were slightly abstract, slightly not very rounded off. So to solve it without using log table, I have rounded off some of the data to simplify the calculation. So after doing this weak acid, especially weak monobasic acid, now let us take one or two cases of polybasic acid. Although the exact calculation of polybasic acid is beyond the scope of this course, because for that we need to solve cubic equation, which is not required at this stage. So we are going to understand the polybasic acid qualitatively, and under certain circumstances we will be solving it with appropriate approximation. So let us take case of weak polybasic acids. Let us start with weak diabasic acid. Examples of weak diabasic acids are oxalic acid, H2C2O4, carbonic acid, H2CO3, H2S, orthophosphorus acid, H3PO3, etc. They are the common weak diabasic acid. If we take a case of, so before we take any case, let us generalize them by the formula H2A, where H2 represents 2 ionizable hydrogen for diabasic acid. So the ionization of diabasic acid can be expressed as H2A ionizes to give H plus plus HA minus in the first step, and then HA minus ionizing in the second step to H plus plus A2 minus. For first step of ionization, we define K1, which is equal to concentration of hydrogen ion into concentration of HA minus divided by concentration of H2A. Similarly, K2 can be defined as concentration of hydrogen ion into concentration of A2 minus ion divided by concentration of HA minus. Let us call them equation 1 and equation 2. Now, if we have, say, initial concentration of H2A, some C, and if we say that out of C, x mole per liter of H2A has been ionized, so it will produce x mole of H plus and x mole of HA minus. But out of this x mole of HA minus, some y mole of HA minus will be ionized further to produce y mole of H plus and y mole of A2 minus. But in solution, common ion will have common concentration. So, in solution, concentration of hydrogen ion will effectively be x plus y, x from first equation, y from second equation. So, x plus y, and the concentration of HA minus left in the solution is x minus y. So, here we also write x minus y. So, now in the expression K1 and K2, if we substitute the value of concentrations of H plus, HA minus, H2A, it appear initially that there will be two equations of K1 and K2 with two variable x and y, which can be solved algebraically. Of course, that can be solved algebraically, but it will not be easy to solve them without any approximation, because the equation will become cubic and it will not be easy to determine the cube root or value of x or y, x and y. So, what we can do with the knowledge of K1 and K2, it has been observed that in most of the cases, K1 is much greater than K2. K1 is much greater than K2. So, in solution, the major contributor of hydrogen ion will be the first equilibrium. Second equilibrium will not contribute significantly the concentration of hydrogen ion, or we can say that y will be much smaller than x. If it is the case, then for calculation we can assume it like monobasic acid, in which second ionization is insignificant. So, if second ionization is ignored, we can apply the approximation as we did in the monobasic acid in case of monobasic acid. So, let us rewrite with this approximation that the acid will be ionized in first step significantly. So, ignoring second ionization, this can be written as H2A giving H plus, HA minus, and K1 is now H plus, HA minus upon H2A. Now, C is the concentration of H2A, alpha is the degree of ionization in the first step. So, it will be C alpha, C alpha, C alpha, C alpha as in case of monobasic acid. So, once again K1, now K1 will be equal to C alpha into C alpha upon C into 1 minus alpha. So, the same equation C alpha square upon 1 minus alpha. So, what we need to do the same thing we did for monobasic acid, that is, we will first determine approximate value of alpha, which will be equal to root under Ka1 upon C. And once again, if alpha is less than 0.1, concentration of hydrogen ion will be equal to root under K1 into C. This all we are repeating the weak monobasic acid case. So, here we determine the hydrogen ion concentration, and taking negative log of that we can determine the pH of solution. One more question is usually asked in case of diabasic acid, that what will be the concentration of A2 minus, what will be the concentration of A2 minus here. So, for concentration of A2 minus, we will have to solve Ka2, which is equal to concentration of H plus into concentration of A2 minus upon concentration of Ha minus. Now, since we are ignoring second ionization in comparison to first ionization, so just we have seen that concentration of H plus is approximately equal to concentration of Ha minus, since we are ignoring second ionization. So, Y is negligible, Y is negligible in comparison to X. So, X plus Y is X, X minus Y is X. So, hydrogen ion concentration is almost equal to the concentration of Ha minus. With this approximation, this 2 will cancel out, leaving Ka2 is equal to concentration of A2 minus. So, that is how we determine the concentration of A2 minus in the solution. So, this is for pH, this is for concentration of A2 minus concept, and all these are based on assumption that K2 is much smaller than K1. So, now let us use them for some calculation. Suppose we have been asked to solve a problem of diabasic acid, given Ka1 of carbon dioxide is equal to 4 into 10 raised to the power minus 7, and Ka2 is 5 into 10 raised to the power minus 11. The question is determine pH of a 0.2 molar CO2 solution, 0.2 molar CO2 solution in water. Also determine the concentration of carbonate ion in solution. It is very straightforward. Just we have derived the expression, we need to substitute the value. So, here is the solution. Since K1 is much greater than Ka2, second ionization can be ignored. In determining in determining pH of solution. Therefore, we just need to check for alpha, which will be equal to K1 upon C. K1 is 4 into 10 raised to the power minus 7 divided by C is 0.2. C is 0.2, yeah, 0.2 under root. So, it is obvious that the value of this alpha is less than 0.1. So, alpha is negligible in comparison to 1. In that case, like we did in monobasic acid, concentration of hydrogen ion will be equal to root under K1 into C. K1 is given 4 into 10 raised to the power minus 7, C is 0.2 and that whole under root. So, it is 8 into 10 raised to the power minus 8 under root. So, pH will be equal to negative log of root under 8 into 10 raised to the power minus 8. So, root will come out as 1 by 2 inside the bracket, negative log 8, negative log 10 raised to the power minus 8. So, it will be 8 minus log of 8. Log 8 can be written as 3 log 2. So, it is 1 by 2, 8 minus 3 log 2. Log 2 is 0.3. So, 0.3 into 3.9, 8 minus 0.9 is 7.1 divided by 2. So, it is 3.55. So, that is the pH of solution of carbonic acid. For carbonate ion concentration, concentration of carbonate ion will be equal to Ka2, we just derived 5 into 10 raised to the power minus 11. So, that is going to be the concentration of carbonate ion. So, after knowing the concentration of carbonate ion, we complete here the solution of weak acid. Next, we move to solution of weak bases. Solution of weak bases. Weak base are ammonia and all amines. They are the common weak bases we encounter in ionic equilibrium. Ammonia and the amines. Ammonia being a gas, when we dissolve it in water, it forms ammonium hydroxide, which ionizes to give ammonium ion and hydroxide ion. So, ammonia when dissolved in water, it can be written to form first ammonium hydroxide and then it will ionize reversibly to give ammonium ion and hydroxide ion. So, in the question, if it is given that concentration of ammonia, so if C is the concentration of ammonia, that C will become initial concentration of ammonium hydroxide. Now, repeating the same procedure and as in case of weak acid, if alpha is the degree of ionization of this weak base, C into 1 minus alpha will be equal to C alpha, C alpha. Now, if we define an equilibrium constant for this ionization process Kc, it will be equal to concentration of ammonium ion into concentration of hydroxide ion upon concentration of ammonium hydroxide. Substituting the value in term of alpha and C, it will be C alpha divided by C into 1 minus alpha. So, if we cancel 1 C, it will be C alpha square upon 1 minus alpha. So, expression is same as in case of weak acid. For weak base, this Kc has been given a specific name Kb, and we read it ionization constant. Ionization constants of base. Just like Ka, the property of Kb will also be same, that is for a given base Kb will be constant and its value will depend only on temperature. The value of Kb will not depend on concentration of base or concentration of any other species present in the solution. Once again, we will apply the same approximation here to solve the solution of weak base. We will assume first alpha to be negligible. So, if alpha is very small, in comparison to 1 minus alpha can be approximately written equal to 1, with this assumption that Kb will become equal to C alpha square upon 1 minus alpha is 1. So, once again alpha will be equal to root under Kb upon C. Like in case of weak acid, in case of weak base also, the approximate value of alpha can be determined by the similar type of equation, which is once again an Ostwald equation. And same dilution law apply here, that if we dilute the solution, alpha will increase, and at infinite dilution the weak base will be completely ionized. Now, in the similar manner, to solve the problem of weak base, we determine alpha from the above equation. If alpha comes out to be less than 0.1, it will be taken negligible. So, alpha is negligible. This indicates negligible alpha. With this assumption, when alpha is negligible, 1 minus alpha can now be taken equal to 1. Now, if we substitute this in the expression here, in this expression the concentration of ammonium ion and concentration of hydroxide ion are same. Concentration of ammonium ion and concentration of hydroxide ion are same, both are C alpha. So, numerator can be written as OH minus concentration square, and denominator, which is ammonium hydroxide, which is C into 1 minus alpha, will become C with this approximation when alpha is negligible. So, Kb will be equal to concentration of hydroxide ion square divided by C. This implies concentration of hydroxide ion will be equal to Kb into C under root. So, knowing the value of hydroxide ion concentration, first we find out pOH and then we subtract it from the 14 to determine the value of pH at 25 degrees Celsius. But if alpha comes out to be greater than or equal to 0.1, that is alpha is not negligible. If alpha is not negligible, then solve the expression Kb, which is C alpha square upon 1 minus alpha. It is a quadratic equation in alpha, so Kb will be given, C will be given. Solving this expression, we find out alpha, and then we determine concentration of hydroxide ion is equal to C alpha. C will be given, alpha will be determined by solving the quadratic equation. Once hydroxide ion concentration is known, taking negative log of this will give the pOH, and subtracting that pOH from 14 will give the value of pH. So now let us solve few problems based on solution of weak bases. Kb of ammonia is 2 into 10 raised to the power minus 5 at 25 degrees Celsius. So determine pH of a 0.05 molar ammonia solution. Now we have Kb value, we have concentration of base. So first both Kb and concentration are known, so we can check for alpha. Alpha will be equal to root under Kb upon C. Kb is 2 into 10 raised to the power minus 5 upon C is 0.05. It is obviously less than 0.1, so it is negligible. It is negligible. So once alpha is negligible, just we have derived that concentration of hydroxide ion will be equal to root under Kb into C. So Kb is 2 into 10 raised to the power minus 5, C is 5 into 10 raised to the power minus 2. So it is 10 into 10 raised to the power minus 7, so it is 10 raised to the power minus 6 under root. So it is 10 raised to the power minus 3. So hydroxide ion concentration is 10 raised to the power minus 3. Hydroxide ion concentration is 10 raised to the power minus 3. So pOH, which is negative log of concentration of hydroxide ion, will be equal to minus log of 10 raised to the power minus 3, so it will be 3. Therefore, at 25 degrees Celsius, pH will be equal to 14 minus pOH. So 14 minus 3, it is 11. So we solved a simple situation of weak acid, and this is very much like solution of weak acid so far as calculation and approach is concerned. Let us take one more problem of solution of weak base. Given Kb of CH3NH2, which is a weak base methenamine, is 2 into 10 raised to the power minus 4. Also given an aqueous solution of CH3NH2 has pH equal to 10, pH equal to 10. Now, what volume of a 0.01 molar, what volume of a 0.01 molar HCl solution will be required to react completely with methenamine CH3NH2 present in its 500 ml solution. So the question is, that we have a solution of weak base. Let us represent it diagrammatically. We have a solution of weak base whose volume is given 500 ml, pH is given, it is 10, and it is a solution of weak base, so it is better to work out POH, because in expression POH will come. So POH will be 14 minus 10, so 4. Now POH is known, Kb is known. The objective of this question is to find out the moles of this base present in 500 ml solution, so that the moles of HCl required can be determined. For knowing the moles of weak base in this solution, we will have to find out the initial concentration of weak base, that is C. So weak base methenamine ionization can be expressed as CH3NH3OH ionizing to give CH3NH3 plus OH minus. If C is the concentration of this weak base and alpha is the degree of ionization, so it will be C1 minus alpha, C alpha, C alpha. Now we don't know C, so we cannot apply the Ostwald equation to check the value of alpha where it lies. But what we know, concentration of hydroxide ion, which is 10 raised to the power minus 4 molar. So C alpha is known, it is 10 raised to the power minus 4 molar. Since POH is given 4, so concentration of hydroxide ion is 10 raised to the power minus 4, and concentration of hydroxide ion is also C alpha. Now if we write the expression of Kb, the standard form is C alpha square upon 1 minus alpha. So it is C alpha upon 1 minus alpha. Now if we substitute the value, Kb is 2 into 10 raised to the power minus 4 is equal to C alpha is 10 raised to the power minus 4 alpha upon 1 minus alpha. So it will cancel off, giving alpha is equal to 2 by 3. Alpha is 2 by 3, so it is 0.67, much greater than 0.1. It is not negligible. It is not negligible. So once alpha is known, C alpha, which is 10 raised to the power minus 4, implies C is equal to 10 raised to the power minus 4 divided by alpha, which is 2 by 3. So, it is 3 by 2 into 10 raised to the power minus 4 molar. So, now concentration of base is known. Volume of base is given in the question, that is 500 ml. So, millimole of base can be known. Millimole of CH3NH2 is equal to molarity multiplied by volume. So, 3 by 2 into 10 raised to the power minus 4 into 500. It is 3 by 2, 1.5 into 500, 750. So, 0.075 millimole. For neutralizing, for reacting with 0.075 millimole of amine, the same millimole of HCl will be required. So, millimole of HCl required will be equal to 0.075, and that will be equal to its molarity 0.01 into volume. So, if we solve for V, it will be 0.075 divided by 0.01. So, it is 7.5 milliliter. So, if we add 7.5 milliliter of HCl to 500 ml of given amine, amine will be completely reacted, will be completely protonated to form CH3NH3 plus Cl minus salt. So, that is all about the solution of weak acid, weak base, and we have laid down a very strong foundation of ionic equilibrium. The concepts of ionization of weak acid, weak base are going to play very important role in the next topic, that is hydrolysis of salt.